have a semiconductor, and we have these two types of semiconductors. We have a p-type and we have an n-type. So we have our p-type and our n-type. And I think I have these backwards from what's, you can't really read them on the sheet. But that's, the n-type is over there, and the p-type is on this side. Now, how do I know which one is the n-type and which one is the p-type? The way I know is because they are doped with either a electron donor or electron acceptor. So this is made up of some sort of semiconductor, and semiconductors do exactly what it sounds like. They don't conduct as well as a conductor, but they're also not insulators. They conduct a little bit. And the way that they conduct is by the electrons, they have some free electrons that can move, and when they move, they leave behind a hole. And that hole acts like a positive charge carrier, and the electron is a negative charge carrier. But all in all, it's not charged, because you still have the same amount of positive and negative. It's just that you have these charge carriers that can move. And semiconductors, good ones, are silicon, germanium, gallium arsenide, and some others. And they're pretty good. But if you dope them, then they can act better. And if you dope them, you would use something like phosphorus. Phosphorus is an electron donor. Now, when we say it's electron donor, that doesn't mean that it has extra negative charge to give away. It means it's in column 5, if you remember from your chemistry. And so it has these 4 electrons that it's going to be using to make bonds with the silicons, or with the silicons on either side, but it's got 5 electrons, so that extra electron is free to move. And so that's why it's an electron donor. But it doesn't mean that it's negatively charged. It's just this one, this electron is now moving around. Or you can have boron, which has 3 electrons. So it's got an empty space right there. It's a hole. So it's an acceptor. So boron is an acceptor. Acceptor. And so acceptors add holes, which are positive charge carriers. And donors add electrons, which are negative charge carriers. But what happens is right here in the middle, on my negative type, I've got my electrons, and on the p-type, I've got the holes, and then these can recombine. Now, if you remember, I said that it wasn't actually charged. This wasn't really an extra electron. It came from something else that had a positive charge. And so now this negative charge is tied up. And so that leaves the positive charge behind. So on the n-type, we actually have positive charge right here. And on the p-type, we have negative charge right there from what's left behind. So we have positive here and negative here. And the effect of that is to make an electric field that resists the flow of electricity in one direction, but allows it in the other direction, and that's what makes a diode. This region is called the depletion zone, or depletion region. It's also called, it has other names as well. I have some other notes. What's that? Depletion region? Okay. All right. So I'm going to go through the questions I have on this handout. So you're going to have on your test, my understanding, is some short answer and some problems. The short answers that I have for you are harder than what I've seen on the tests. So we're going to go over some easier ones out loud. So let's do let's just do some, and we'll just take I'll take volunteers. Let's say silicon is doped with an acceptor element, for example, boron. So I've doped silicon with an acceptor element such as boron. What type of charge carrier does that add to the semiconductor? Holes, and what sign are they going to be? Positive. Okay. I haven't talked about this yet, well, so I'll say that. What's the name for the area in a, this is called a p-n junction. So like if we're labeling this on the tiny little picture I gave you, that's a p-n junction diode. What's the name for the area in a p-n junction with nearly zero mobile charge carriers? Depletion region. They're not mobile because they're all tied up. Oh, okay. So let's think about the holes can move and the electrons can move. If the electrons, the direction that the electrons move, is that the direction of conventional current or opposite the direction of conventional current? What direction is conventional current? Yeah, because what direction is conventional current? The positive charge carriers. So holes actually move in the direction of conventional current. So that's actually what it is. Okay. All right. Now, if we have this set up like this, so I have this and I have a positive charge here, or a voltage source here in this direction. This is said to be forward biased. And that means the current can go in this direction, and it does. If I had it the other way, that is said to be reverse biased, and very little current flows. Okay. Oh, this was what I was looking for. Is there anything else on here that I needed? Yes. Okay, so we call this the anode, and this is the cathode. So the positive side is the anode. All right. All right, so let's take a look at oh, okay. Another thing that you need to know are the different types of diodes. So let's make sure we recognize them. And we'll talk more in a minute about what the differences are. Sorry, it's a terrible drawing. Okay, so this one is a Zener diode. This one is a Schottky diode. This one is an LED, a light emitting diode. This one is a varactor. And this one is a photodiode. And I have to look something up for just a minute while y'all are drawing these. Okay, how many of you actually have a textbook? All right, that's the way. That's what I like to hear from your generation. It is actually. I'm serious. Not going to pause it. The textbook companies keep raising the price and raising the price and raising the price, so people don't buy them, and then they don't buy them some more. So they think the correct thing to do is raise the price some more, and that just doesn't happen. So I'm going to take a picture of the pages that describe these different types of diodes, and I will just.
I have a PDF of the textbook for this class if you.
Oh, I have a PDF as well. Yeah, but I was gonna like to send to y'all. Yeah, because I don't want to send the whole. I don't know how many of you have a PDF. I mean, that's okay. So not many of you have that either. Just rather than defining each of the type of diodes, I just thought that might be quicker. Yeah, it'll be quicker. How many of you are in circuits 2? How many of you are not in circuits 2? Okay, I'll send it out to the circuits 2 email list, and I'll have a description of each one of the diodes. Okay, so just rather than my going through all of them. All right, let's talk a little bit now about op amps. Okay, so an op amp has, thank you. An op amp has, an ideal op amp has certain characteristics. And those characteristics are that the voltage at the positive terminal and the voltage at the negative terminal are the same. V plus equals V minus. But it does not mean that they're zero. It just means they're the same. However, the current, wherever it's coming from, I'm just making something up, it's not important. So the current IP, the current into the positive terminal and the current into, or I plus. Do y'all use I plus or IP? I plus. So I plus and I minus are equal and 0. And you can use that information to solve a lot of things with op amp problems, and we're going to do some op amp problems in a moment. So what I would like to do right now is to spend, I'm going to pause the recording and spend about 5 minutes with you at your tables or just like people around you. Look at these 12 short answers and see if there's any of them that you can figure out, all of them that you can figure out that you can or can't. But when we come back, remind me that I want to continue recording this. I don't know why, because everybody's either on Zoom or here, but I'm recording it anyway. So just remind me to turn that back on. For those of you on Zoom, just look at these true-false answers and short answers and see if you can figure them out. Okay, so which side is the cathode and which side is the anode?
Anode is the positive one at the bottom.
This one is this is the cathode.
Oh.
I'm sorry, you're right. Yeah, sorry. Anode is at 0.5 and the cathode is at 0. Okay, so this one I hadn't gone over yet. So this is false, but the reason it's false is not because because the signs are wrong. It's because you need to have 0.7. You need to have 0.7 to be forward biased. So this side needs to be 0.7 higher than the other side. So this is not yet forward biased. So so that's why that one is correct. So it does not conduct significant current until we get to 0.5. So until we get to 0.7. So at 0.5, the current is pretty small. But if it is conducting, so if I have a diode and current is going through it, then I know that this side is 0.7 volts higher than this side. 0.7 volts. That's for a regular diode. Okay, true or false, in a reverse bias diode, the current is essentially 0 until breakdown. True or false?
True.
That one's true. What is breakdown?
When it heats up so much that it starts breaking down.
So breakdown is when there's enough of a field to counteract the potential that's being caused by the potential from the depletion region. So so that's why it's called breakdown. It's the same thing, same idea as when have you ever seen those Van de Graaff generators that if you hold your hand of it like makes a spark and makes your head, okay, but when you hold your hand of it or close to it, you see the spark. That's because you break down the air. The air is an insulator, but you break it down to where it becomes a conductor, and that's what that is. So okay, all right. Number 3, 2 primary differences between a Zener diode and an ordinary silicon diode in terms of their voltage current characteristics. What does a Zener diode do? Do y'all know? Have you done problems with the Zener diode? Oh, you haven't.
Regular diodes, LEDs, and photo diodes.
Oh, okay.
The only thing he's said about Zener diodes so far is that they have a predictable breakdown behavior.
Yes. Okay. Well, that's going to change the problems I'm going to do then. So, Zener diode basically it's designed to operate in breakdown, and that's pretty much all you need to know about it. So they have a controlled breakdown. So regular diodes you're not expecting necessarily to have it go reverse bias, but Zener diodes you do. But that's all you need to know about it. Okay. True or false? In an intrinsic or undoped semiconductor, the electron concentration equals the hole concentration.
True.
That's true. That's why you dope it to change that. True or false? At very high temperatures, a semiconductor can behave almost like a conductor due to increased carrier generation. That one's true. And this is a main difference between semiconductors and conductors. What makes a semiconductor conduct? So thermal carrier generation, yes. Okay, so what happens is you create those holes in free electrons. And the hotter you get, the more of those you create. And there's a formula for that that I never saw that y'all ever had to do any problems with that, so we're not gonna worry about it. But the hotter you get, the more of those charge carriers you get. With a regular conductor, the hotter you get, the worse it conducts. So, and there have been questions on this on previous tests. So semiconductor, as temperature goes up, conduction goes up. Conductor, as temperature goes up, conduction goes down. Briefly explain why a p-n junction has a built-in potential across the depletion region even with no external voltage applied. Just briefly. Yeah.
Is it because of the nuclear?
And where does that come from? I mentioned it earlier. Yep.
The moving charges from the carriers to the holes, the movement of the electrons creates a magnetic field.
I don't want to say you're wrong, because moving electrons, yeah, no, yeah. That's not what creates this one. Yeah?
Is it probably because the holes push back on the electrons that must be because it would float so fast and then the electrons pushing
No, y'all are thinking too hard. Okay, so, or maybe not, I don't know. So right here, okay, remember that it starts off electrically neutral, because for every electron, there is a proton, so it's electrically neutral. But then at this depletion region, some of the free electrons join with a hole from, some of the free electrons from the n-type join with a hole from the p-type. That leaves behind a positive charge right here. So what you are left with are positive charges that are not bound. So you have excess positive here and excess negative on this side. Yes? No? Yes?
Is that the diffusion?
Yes. Yes.
Is that what that causes diffusion? Is that what causes the diffusion? When you mentioned like the design or
Yes, it is. So, diffusion, so here's a clear answer. Diffusion of electrons and holes across the p-n junction leaves behind charged ions. This forms a depletion region and an internal electric field which creates a built-in potential even with no external voltage. And I guess maybe I'll post this to YouTube so then you can come back and look at it. And that's why I'm recording it? Yeah, that's why I'm recording it. All right. Okay. True, false. The forward voltage drop of a typical LED is always 0.7 volts, just like a silicon diode. False. LEDs typically have forward drops of 1.8 volts to 3.3 volts or more, depending on the color or material. A photodiode is operated, you probably didn't talk about this, if you didn't go, no, you did. A photodiode is operated in reverse bias to detect light more efficiently. True or false? Yeah, that one's true. That one's true. And Zener diodes, let's see, the breakdown voltage of a Zener diode is often quite low, 5 volts, whereas typical avalanche breakdown diodes, that just means typical diodes, require much higher voltage. Is that true for a Zener diode? It is true. So Zener diodes, their breakdown is at a lower voltage than other diodes because they're designed to do that. Describe the role of the depletion region in a p-n junction. It's where mobile carriers have diffused away. So depletion region. have diffused away. Leaving behind charged ions. And when you're forward biased, it narrows. Because the charge more easily flows. And in reverse bias, it widens, inhibiting flow.
Wait, what is that about mobile carriers?
Leaving, whoa. What was the question? Something about carriers? Mobile carriers. Yeah.
Yeah, what does it say about mobile carriers?
It says mobile carriers have diffused away, leaving behind charged ions.
Okay, thank you.
You're welcome. Let's see, what's next? In an N-type semiconductor, an N-type semiconductor has positively charged donors that compensate for the extra electrons, making the overall crystal charge neutral. This is tricky. This one is true. So why is it true? Because our donor, it's a donor, so it's like phosphorus. So this is N-type. So phosphorus has 5 valence electrons. It's donating this 1 electron to go travel around and be free. So that means it's leaving behind a positive rest of the ion. And so this one is true, that an N-type semiconductor does have positive ions left behind. So the overall material is neutral. For every negative, you have a positive. True, false. In a half-wave rectifier circuit, the diode conducts for the entire cycle of the AC signal. That one's false. It's given right there in the name. It conducts only during half of the AC cycle. Okay, let's see. All right, so let's do some problems. Y'all ready for some problems? Let's see, 6:16. We started at 5:30. A little later, 5:45. Okay. Let's take like a 5 or 10 minute break, because this room, is it really hot or is it me? It's warm. Let's take about a 5-10 minute break. There are bathrooms that you really do have to flush like 4 or 5 times to make them work. Just really do. There's bathrooms there. There's a water fountain. Just if you need to get up and walk around. Let's just take a little break. Let's say we'll start back at 6:25. 6:25.
Also, are you going to go over the 3 types of diode problems for most likely? Because there's 3 methods he likes to do: exponential and
So I haven't done the problems yet.
Okay. No. I'm curious. It's just like, is that something like, that?
I'm deciding right now. So I'm going to be doing. I'm definitely doing exponential. Probably doing. What else were you asking about?
It's like constant, like.
Yes, I'm doing that one.
And there's also like ideal.
Probably not doing ideal. Ideal is easy. Ideal is just If it's going, like, if it's forward biased, it's just going forward. If it's reverse, it's reverse.
And the other one that I do not know the name is just it's just assuming there's a voltage drop of 0.7.
Yeah, we're doing that one.
Okay, perfect. That's because that was like one of my biggest confusions.
Okay, yeah, we're doing that.
Also, drawing and drawing a rather a full rectifiable circuit or a halfway.
We might not. It depends if I have time to review them during this little break, because that's what I haven't gotten to myself yet. So I've got like 5 minutes to review it.
Okay. And what about potential monitor? That might not be as important.
I don't think it's as important, but if maybe. You're just looking at what's on the old test.
No, problem set.
Oh, wasn't the problem set? It was a problem set, wasn't it?
Yeah.
Yeah, okay.
Actually, with the old test, I've never seen a potential monitor.
Okay, then I don't know if I will or not. We'll see. Okay. But I'm definitely doing the constant drop and exponential models.
No, I'm taking it right now. At home with me tonight. That plus the electronics lab that I totally meant to do. Oh, yeah.
Okay, so phosphorus
Well,
is it in
for
type?
Digitu, oh, okay. So apparently the group ahead of me likes to break everything at my station. So they burned part of my trainer kit. And then Verilog just flooded the whole sucks.
Wait, how many things like
Yeah.
And can you give away one?
Yeah.
So you walk in the classroom and you go to fall all the way at the end to the left and it's not working. Or it's like working weird.
Guess which one I'm using?
Yeah, you can. That's the one with me.
Yeah, did you see that picture of the bird box over the the one that looks like it has citizens on it? Like the birds, look like bird sheds and stuff? I think it's really fun.
I'm gonna spend like at least 15 minutes finishing up. Like I got all the graphs for my lab report. I just need to write stuff down. I just need to write stuff down.
No breakfast. No breakfast. At 7:30 I can't actually.
I'm probably not gonna do
Yeah,
that.
that's what. Every day last semester I actually made like an actual breakfast with eggs and maybe toast.
I took one. What my time might change like this FYI.
Before the class, but since they will have to make that. So it's only during the lunch and yeah, just get a bunch of errands like a month ago and I ran out and have a lot of because I'm so busy doing school. Anna's do the grocery run. We'll have to
Okay, let's see, it's 26. No, it's not. I said 26.
It mirrors side hook, description, and a few others. Right, someday I'm going to see I want to do a whole I really like
I just feel bad.
it's like it's kind of the side of information so we're going to scale which I think is wonderfully chaotic.
Oh yeah. Yeah, that's whenever I saw that, I was so happy. Wow, so hyped. So
well, I come from I haven't even it's actually kind of funny to find
Oh, that's
now you'll finish it.
or no, so he didn't go to high school there. He like I met him at my high school. And he's like, oh yeah, no. Well, there's the inverting and non-inverting. So it takes the different walls, right? So general areas for most practical purposes.
Kind of until I feel like there's nothing more I can do.
Okay, so I mean, typically, feedback is positive or negative.
It wasn't as hard before semester. Like people were kind of down.
If you're grounded,
That's kind of, I plan on being
running the yeah, because I need to like sleep and back to
I mean, if people don't want me, I'm
we're gonna have I'll join he was good negatively and I'll just
All right. So let's get back. And we're going to do some problems. And just, full disclosure, I took electronics in 2013.
Was it harder back then?
I don't know. It was different. I liked it a lot. Dr. Choi was great. So I don't know if it was or not. It seems, as far as I can tell, is pretty similar. From what I've seen, the kinds of questions that I think are going to be on your test are similar to the kinds of questions we had. We had a page of short answer. It was basically true, false. Oh, although he was sneaky. You could choose not to answer and get a point, or answer it and get 2 points, but if you got it wrong, it was like minus a point. Yeah.
So, I mean, I guess it has the same expected value, but that's terrifying.
Yeah, it was terrifying, correct, yes. Yeah. So, but it was true, false, and but you had to explain? I can't quite remember, but anyway. All right, so here's our first problem. We have a 9-volt source that feeds 2 resistors in series, 2 kiloohms and 8 kiloohms. The junction between R1 and R2 goes through a standard silicon diode, and we're given IS to the ground. So we've got, we draw it the way, and this is one thing I did not like about electronics, is the way they draw things. It's just, I don't like it, but that's me. Okay, so we have, wait, that's can't be right. Okay, so we're supposed to use the constant voltage drop model. I'm not sure, I'm looking at this problem, I'm not sure I have this drawn right. We'll see as I work through it if everything is the way I think it is. Okay, you're supposed to use the constant voltage drop model to find the diode current. So that would mean that VD is 0.7 volts. Now, if we do voltage division on the two 2 kilo ohm and 8 kilo ohm over here, and I get V right there. V equals 9 times 8 over 8 plus 2, or 9 times 8 over 10, or 7.2 volts. So that's what V would be if the, y'all can't see, I'm covering it up on my monitor, y'all can't see that. If the diode weren't there, then V would be 7.2 volts. Now we're going to get the parallel combination of the 2 kilo ohm resistor and the 8 kilo ohm resistor. So 2 kilo ohms in parallel with 8 kilo ohms is 2 times 8 over 2 plus 8, which is 1.6 kilo ohms. And that would be R Thevenin. think I have this drawn wrong. I'm not sure how it's supposed to be drawn. Give me a minute to figure this out. I need to have some resistance in here. This is... Yeah, everything, if the diode's not here, everything is fine, but let's see. Let me do a different one that I know I have the drawing for. Let me get one that I know I have the graph for. So hold on.
We just use the CPD. Or, oh wait, we are just using CPD, aren't we? Yeah. Oh, yeah. Were we planning to turn into it? Yeah. At the same time. Okay, so that's probably right. I think we're talking about working two resistors in series, 9-volt source. Not necessarily. But we would end up wanting to buy if we're using a custom voltage drop model that allows us to just so you can just
I'm gonna do this one instead. I can do this one instead because I know I've got this one drawn right. It's very similar, but it's got another resistor, which... Okay, so I've got this one, and I'm going to use the constant voltage drop to find the current through the 3 resistors on this one. Okay, so... So the first thing I want to do is find the Thevenin equivalent as seen from the diode's anode. So the Thevenin equivalent as seen from the diode's anode is going to see these two in parallel. And they're going to be in parallel because the Thevenin equivalent is going to make short out the voltage source. And so these are to make it ground. And so these will appear to be in parallel. And so we're going to get the equivalent resistance. So 4K in parallel with 12K is 4 times 12 over 4 plus 12, which is 48 over 16, which is 3K ohms. Now we're going to assume that VD is 0.7 volts. And that's because we're using a constant drop model. Then the next thing that I need to do is to find the voltage right there. And so the voltage right there is as if this part was removed. As if this part was removed. So we can use voltage division. So we can get V equals 10 times 12 over 16, or V equals 120 over 16. Does someone have a calculator? 7.5. Okay, so we know this is 7.5 volts. So we know we've got 7.5 volts right there. So what is the voltage on the other side of the diode? It's going to be 7.5 minus 0.7, which is 6.8. So then the current through the 2K resistor will be 6.8 over 2,000. And y'all should all check me because I am known for not being able to use a calculator. 0.0034 amps. The current through the 4K resistor is 10 minus 7.5 over 4,000. Which is 0.000625. And the current through the 12K resistor is 7.5 I don't have much open. Oh, MATLAB. Close. Will be 7.5 over 12,000. .00625 amps. Okay, so that is using the constant drop model. Now let's use the exponential model. Yes?
What's the point of doing R7 to get the 3K
Oh, good question. Because I did it wrong. Hold on. Yeah, I messed up. Yeah, I messed up. So, hold on. I needed that and I didn't use it. I needed that. Yeah, I did the same thing this morning. Sorry. Okay, so everything is correct up to the R Thevenin. And then, well, I can't use voltage division. I did use I said pretend like that's not there, but I don't know why I would.
That's how you find
V Thevenin.
Because you ignore the diode and the open circuit.
Right. Hold on.
If you were to put that circuit that you have over there, you would also you're actually trying to have been voltage.
I am going to be using the Thevenin voltage. Yes, yes. So hold on. So this is what I should have done at this point. Is I should have taken my my 10 volts and my Thevenin voltage. I mean my Thevenin resistance, which was 3K. And then my diode, and then my 2K.
Doesn't the voltage change to 7.5?
Doesn't which voltage change? Does this?
The 10 volts.
The 10 volts changes to 7.5. Okay, yes.
Why would the Thevenin analysis not include the 2K? Couldn't that be simplified with the 12K to get, or with the 3K that you got from the other part of the Thevenin to make a 5K resistance for ground?
You mean change this 3K to a 5K?
And then get rid of the 2K, because those grounds would be connected in the same way, and they would just be in series with the other part of the Thevenin resistance.
I think so. I just hadn't thought that part through. So hold on. Yes, I can do that. I just hadn't gotten there yet. Yeah. Okay, so let me go. I heard confusion, and I don't blame you for being confused. So let me go back and just tell you what, because I messed you up. All right. So we found the Thevenin resistance, which was 3 kilo ohms, and we found the voltage to be 7.5. We found the Thevenin voltage to be 7.5. So at this point, we're going to transform it and look like this. So we have the 7.5 voltage and the 2K resistor, as we were just talking about, is connected to ground, as is our Thevenin resistance. And so we can combine those in series to make a 5K. But now I'm getting all messed up. Let me come back to this problem and do one I'm certain of. I'm sorry. I'm going to do one that I know I'm certain of, and then we'll come back to this one. All right.
The one you have there, the extra resistance, which wouldn't necessarily be, if you were to solve it using voltage description, or the same method I think there, but
Yeah. Do you feel confident to come up and explain it? Because I'm happy to let you do that if you want to. Because I'm like.
Oh, sorry. I thought you said a different name.
No,
Explain.
the problem that I was like put aside for right now.
Oh, I wouldn't feel super.
Okay, that's fine, that's fine. Okay, I'll come back to it after I've let my brain think on it for a little bit. Okay, all right, so let's say we've got this op amp, and we've got a diode, and we have V in, and we have V out, and we want, the first thing that I want to do is to find an expression for V out in terms of our resistor and and using the diode properties. Now you do have a formula sheet, and your formula sheet has the exponential model for a diode. What is the exponential model for a diode?
How that be?
Okay, so that is that's our exponential model for the diode. Okay, what do we know about an op amp?
V minus equals to V plus.
Yep,
I plus equals to I minus equals to 0.
yep. Okay, so what do we know about this voltage right here, V minus?
It's equal to 0.
It is equal to 0. So what is VD? What's the voltage? The voltage on this side is 0, and what's the voltage on this side? V out. So VD, not VD is V minus V out. So we have that I diode equals IS E minus V out over VT. Okay, so can we figure out anything about the current?
Well, it's equal to VN. It's equal to VN divided by R.
Yeah, so this current Vn divided by R is going to be our current. And how did you get that?
Ohm's law with the resistance.
Yeah, so we just have that. All right. So I can say that I diode, is that the same as is that going to be the same as the current through the diode?
Yes.
Why?
Because the current, I minus current is equal to 0, so it's just flowing all back to the diode.
Correct. So that has to be Vn over R. Or divide by IS equals E to the minus V out over VT. Take the natural log. Vn over RIS equals minus V out over VT, or V out equals minus VT times the natural log of Vn over RIS. That's all there is to that one. Let me find another one. Yep. Yep. Yes.
For the exponential diode equation on our formula sheet, there's a little -1 after it.
You can usually ignore the -1.
Okay.
Yeah, I just remember that. I don't have an answer for you, but I just know that you usually ignore it.
Because it doesn't, the changes are insignificant.
Yeah, the EEC is so large, the -1 could be that many difference.
Okay, let's do another one. Okay, I'm going to make sure I get this right. Okay, so I've got this circuit right here. And VA is 3 volts and VB is 1 volt. We're going to use the I'm going to use the constant drop model, and we're going to figure out what Vy is. So does anyone recognize this circuit? It's an OR gate. What does an AND gate look like? Flip both the diodes. Flip both the diodes. Okay, so how do we determine what the voltage is at Y? First have to determine the biases. And how do we determine that? I don't have a good answer. I just do guess and check. So we're saying VA is 3 and VB is 1. So can they both be on? No, they can't both be on. So let's say B is on, but A is off. Then what would the voltage be over here? 0.3. 0.3. But then that one would be on, because 3 is bigger than 0.3 by more than 0.7. Okay, let's go back, make sure everybody understands. Does everybody understand why they can't both be on? No. Okay, they can't both be on because then the voltage on this side would have 2 different values. And it's all connected. It can't have 2 different values. So they can't both be on, because if they were both on, the voltage over here would be 2.3 and 0.3. So then we assume one of them's on. So I assumed the bottom one was on. That would make this 0.3. So if this is 0.3 and that's 3, then the top one would be on. But we said the top one was off. So it can't be that the bottom one is on. So the bottom one has to be off. Well, let's make sure that works. If the bottom one is off, then we have this is 2.3, and this is 2.3. Does that agree with the bottom one being off? Yes, because the anode is not 0.7 more than the cathode. So then that gives us that Y is 2.3 volts. Some of you like that, some of you don't. You don't like that? Let's try it. Let's try an AND gate and see if it helps. Notice I'm retreating to my digital logic comfort zone. But I hated it when electronics intruded into my digital logic comfort zone. Okay, say this is 0.6 volts up here. And A is still 3 volts, and B is 1 volt. Okay, so we need to figure out the voltage at Y. So let's assume that the 3 volt diode is on. Then what does the voltage have to be at the other side of this? It needs to be 3.7. But if it is 3.7, then this one is also on, which would mean it'd have to be 1.7. And that can't be. Can't be both 3.7 and 1.7. So let's say the bottom one is on. What does the voltage need to be on this side? 1.7. So then, is the top one on at all? It's not on. And we have a voltage of 1.7. Okay. Let's try one from your homework.
Can you do the one with the op amp and the yeah, in like a really
Oh, the potentiometer? Y'all want that one or not want that one?
Yes.
If I can find it.
I was right.
It was, unless, you know.
Which homework was that?
It's the second one, problem set 2.
Uh, I think I lost the problem. Can you describe it to me?
guess the problem set answers.
Yeah,
I have the answers. Is it the same? Is it drawn on the answers?
I can draw it out for
Oh,
you.
I have
Okay.
it. I have a picture of it.
Oh, okay. Yeah. Let me just see it. Let me just see it. That's it. Yeah, that's it. Okay.
I heard that too from someone.
And then what other information was given in the problem?
The forward drop is 4 volts. I have is 20 milliamps.
And what are we asking for?
The current for the diode, I think.
Maximum current.
Okay, so the max and minimum. Okay, so we know that we have what is a potentiometer? It's a variable resistor, and we know that V plus has to equal V minus. And this is 10 volts. And if we have the maximum, if we make this voltage, if we get the potentiometer down to where we're getting the full voltage, then we could have 10 volts. So then our max voltage would be 10 volts. And if we have 10 volts, then we would also have 10 volts here, which would be 10 volts here. What's our current in this wire right here? 0. Has to be 0 because it's the current going in to the negative terminal. So that means the current that's going down through the resistor has to be the same as the current through the diode. And so 10 minus 0 over 10 equals 1 amp. That would be our maximum current through the diode. All right, now our minimum would be if we get this was a LED. Yeah. If we get the potentiometer all the way up to 100K, then the voltage, well, just think of it as moving this arrow up and down. So if you move it all the way to this side, that's going to put it, get like all of the resistance, and you're going to get at a voltage of 0. But you could also, I mean, that's the way the potentiometer works. You get a portion of that resistance, and so our minimum voltage that we would get is 0. So if we have 0 volts, then we have 0 volts here, and we have our min current is 0. Okay, so now we need to, can I see, does anyone have a formula sheet? So do y'all have a formula like this?
No.
No. Okay.
But it was powerful, like you did something like that on your homework.
Mm-hmm. Okay. Thank you.
That one's the one that's giving us like I don't necessarily know why. I think it might be.
Okay, so I have that IS equals ID over E to the VD over VT. Or ID equals IS E to the VD over VT. And we were given VF is 2.4. So ID was 1 amp. And IS, we were given IS, but let's see. And then E to the 2.4 over VT is usually 0.025. What am I supposed to be solving for? I don't even remember.
The first part was the maximum current, then you're finding the maximum voltage through the diode. Then you are finding the maximum supply needed by the op amp in order to make this circuit work. So it would just be the...
Oh, okay, I see. Now I understand. I was really confused. Okay, I get it. Okay, so we're trying to, can you read that again?
No, I just had my answers.
Oh, can someone read the problem? Because I didn't know what I was solving for. Can someone read the problem out loud? I don't have the problem in front of me, so I don't know what I'm solving for.
Yeah, I'm pointing out.
The next part is VT.
Right, I'd like the actual wording so that I can, yeah.
It's kind of a long one.
Okay, so here's the wording. So I need the maximum positive supply voltage needed by the op amp to support the maximum current through the LED rounded up to the nearest volt. So the maximum positive supply voltage needed by the op amp. Okay, so thank you. So I need the gain to be enough to get my 20 milliamps up to a full amp, because that's the maximum current that I can have. And so I need to figure out what I would multiply 20 milliamps by to get 1 amp. So if I had 20 milliamps, which is what we're given, equals IS e to the VD over VT, then I'm going to multiply both sides by 50 to get to 1 amp, because that's my maximum current. And then, in order to get this to a way that we can solve it, we're going to get this 50 up into the exponent up here with the VD and the VT. The only way to get that up there is to rewrite it as e to the natural log of 50. Because e to the natural log of 50 makes this 50, gets it up into the exponent. So now I can write this as IS e to the VD over VT plus the natural log of 50. So now you can write this as e to the VD plus natural log 50 times VT, just getting a common denominator, over VT. Now if you compare this to our formula, IS, I don't think he's going to give you one like this on the test. IS e to the VD over VT, we now have a new VD. So our new VD is our original VD, so VD new is our original VD plus the natural log of 50 VT. And then you can plug in, and that gets you the numbers that you need. But I don't think he's going to give you one like this. I haven't seen anything like this on this test. Okay, so I was going to do a more basic one from the homework. So let's do this one. Let's sketch the voltage, the output voltage waveform from any of these from problem set 1. Y'all pick one of the ones from problem set 1 that you would like me to do. Anyone?
I'm open, you can play.
Or are y'all all good with problem set 1? No. Problem set 1. Problem set 1 I'm real good with, so if anybody has any on problem set 1 that you would like me to do.
Is there any diodes?
They're all diodes.
How do you look at it?
Okay, I'll just pick.
Wait, two.
But that's not problem set 1 yet, so let's hold on with the rectifier.
Number 2, I guess the hardest number 2 you can think of.
The hardest number 2 I can think of. They're all about the same. 2C.
Okay. ideal diode problem sets, by the way?
It says exponential model.
Oh, perfect.
Oh, that's not, is that C? A, B, C? It doesn't matter, it's the one I'm doing. Okay. Okay, from the point of view of the diode, those two resistors, if we're going to get the Thevenin equivalent, those two resistors are in parallel. So let's get the equivalent resistance. So it's going to be 3 times 1 over 3 plus 1, which is 3 over 4K, which is 750 ohms. So we can redraw it. So we have 5 volts, and then we have our diode. Then we have our 750 ohm Thevenin equivalent. And then we need to get our Thevenin voltage right here. So we can do a voltage division. So 10 times 1 over 4 is 2.5 volts. So our voltage here will be 2.5 volts. So what we did was we first found the Thevenin equivalent. So we found the Thevenin equivalent resistance of these two. And from the point of view of the diode, they're in parallel. So we found them in parallel. Then to find the Thevenin voltage, we did voltage division, and we got 2.5 volts. Now we're going to say that we're going to use our...
Where did the 1/4 come from?
The 1/4 came from 1 over 1 plus 3. So to find the voltage right there, so this is R1, this is R2, and this is, draw this better. So this is R1, this is R2, this is ground, that's my total voltage. To get the voltage right there at R2, it's going to be the Thevenin. The Thevenin is going to be my total voltage times R2 over R1 plus R2. So I took 1 over 1 plus 3, and that's where I got the 1/4.
Okay, thank you.
You're welcome. Okay, so now what I'm going to do is say the current from the top all the way to the bottom is going to be, on the other side of the diode, it'll be 5 minus 0.7. So that's the voltage right there, 5 minus 0.7. And then to get the current through this bottom part, it'll be 5 minus 0.7 minus the voltage on the other side, which is 2.5, over the resistance, which is 750. So that is my current. So 5 minus 3.2 over 750. And no, I'm sorry. We're trying to find VD. We're not assuming it's 0.7. Sorry, that's constant drop. It's VD. So it's 5 minus VD minus 2.5 over 750. And then we're going to use the exponential model and say that that has to equal IS e to the VD over VT. So now I have an equation, but it's difficult to solve, so you can solve it using iteration. I don't know, how do y'all solve these? Okay, I mean, I would use my calculator to solve it. Does he allow that?
Yeah,
Okay, okay.
we're allowed a calculator. He said he was gonna teach us the graphing method, and then he didn't, so.
Oh, do y'all, yeah, it's easy. Do y'all not know how to do that?
Well,
Do y'all have graphing calculators? How many of you have graphing calculators? Most of you? Yeah. So all you have to do is put one equation in y1 and the other in y2 and find out where they intersect. You put one side in y1, one in y2. Yeah. Newton's method works fine. I've gotten to the point that I don't like to use numerical methods when I can use technology. Oh, I have to go. I'm late. But yeah, so to use this, you just put in. It's not even working. You put one in y1 and one in y2, and then you solve. Yes.
What do you exactly set for it to be in y, and what are you doing?
One side of the equation, other side of the equation.
Oh, okay.